The Wärtsilä RT Flex 96C diesel engine aboard the Emma Mærsk weighs 2,300 tons, stands 13.5 meters tall, stretches 26.59 meters long, and once running at full load, burns through 250 tons of heavy fuel oil every 24 hours. Yet shutting it down at sea would cost more in damage, danger, and mechanical destruction than leaving it running for months straight. Each of its 14 cylinders has a bore of 960 millimeters and a piston stroke of 2.5 meters, meaning the internal components expand and contract across thermal ranges so extreme that a cold restart without hours of preparation can crack a crankshaft that weighs 300 tons and took 8 months to forge. On March 26, 2024, the container ship Dali lost electrical power for less than 4 minutes while departing Baltimore. And in that interval, without propulsion, without steering, without bow thruster authority, she struck the Francis Scott Key Bridge at a displacement of 148,984 tons and killed 6 people. The gap between a running engine and a dead one is not a matter of convenience aboard a vessel this size. It is the gap between controlled navigation and uncontrollable mass. The Emma Mærsk, first of the E-class container ships built by Odense Steel Shipyard in Denmark, was laid down on January 20th, 2006, launched on May 18th of the same year, and entered service on August 31st, carrying a crew of 13 in a superstructure capable of housing 30. Her length overall is 397 meters, her beam 56 meters, her molded depth 30 meters from deck edge to keel, and her summer draft 16.02 meters dimensions that give her a gross tonnage of 170,794 and a deadweight tonnage of 156,907. She was, at her commissioning, the largest container ship ever constructed, with an official Mærsk-rated capacity of 11,000 TEU at 14 tons per box, though standard TEU calculations place her true maximum closer to 14,770 containers. Her single fixed-pitch propeller, manufactured by Mecklenburger Metallguss GmbH in Warren, Germany, measures 10.3 meters in diameter and weighs 113 tons. That propeller connects to a main shaft 150 meters long, longest propeller shaft ever installed on a commercial vessel, which runs from the engine room positioned amidships all the way aft, a design choice that maximizes hull rigidity and cargo volume simultaneously. The engine itself, a Wärtsilä 14RT-Flex 96C, is the largest reciprocating engine ever built. Its 14 pistons each weigh 5.5 tons and stand 6 meters tall. The total engine displacement across all cylinders is 25,601 liters. At its maximum continuous rating of 80.08 megawatts, 107,390 horsepower. It turns the crankshaft between 15 and 102 revolutions per minute and produces a torque of 7,603,850 Newton meters. The brake-specific fuel consumption at optimum load is 171 grams per kilowatt hour. The engine uses a common rail fuel injection system that replaced the traditional camshaft and chain gear, allowing electronically controlled hydraulic exhaust valves to manage scavenging without mechanical actuation. Cylinder liner wear runs at approximately 30 micrometers per 1,000 operating hours, a figure achievable only because the crosshead bearing design keeps piston rod forces perfectly vertical, separating crankcase lubrication from cylinder lubrication entirely. Shutting this engine down at sea initiates a thermal collapse that the structure was never designed to absorb rapidly. At operating temperature, the cylinder liners, pistons, exhaust valves, and turbocharger rotors exist in a state of controlled thermal expansion, each component dimensioned to fit correctly only when hot. A shutdown allows the jacket water temperature to fall below the minimum 50 degrees Celsius required for a normal restart. The crankshaft, a single forging weighing 300 tons, contracts unevenly because its journals and webs have different thermal masses. Restarting without a minimum 2-hour preheating cycle risks thermal shock, uneven contraction that creates stress concentrations at the crank pin to web fillets, exactly the geometry where fatigue cracks originate in large marine diesels. The starting air system operates at 30 bar, stored in receiver bottles that must be kept charged by auxiliary compressors that themselves require electrical power from the auxiliary generators. If the main engine is shut down and the auxiliaries fail simultaneously, the vessel has no compressed air to restart, no electrical power to run the lubrication pumps, and no steering authority whatsoever. The Viking Sky demonstrated this cascade on March 23, 2019, off the Norwegian coast near Hustadvika. Her lubricating oil level was low, but within minimum acceptable parameters, when heavy seas caused the oil to slosh away from the pump suctions. The resulting low oil pressure triggered an automatic safety shutdown of all 4 engines simultaneously. With 1,373 people aboard, the ship drifted without propulsion toward a rocky shoreline in storm conditions for 14 minutes before crew could manually refill the lube oil sump and restart a single engine.
How much longer?
The Norwegian Safety Investigation Authority concluded that had the engines been maintained at operating temperature with adequate oil levels, the automated shutdown would never have activated.
Main engine number 1 is online.
The blackout was not
Oil
caused by a
pressure and
mechanical
RPMs
failure.
are stable.
It was caused by conditions that only existed because the engine's own protection system interpreted a transient low-pressure reading as a reason to stop. Aboard the Mærsk, 5 Caterpillar-built diesel generators produce a combined 20.8 megawatts of auxiliary electrical power, supplemented by 8.5 megawatts recovered from a Peter Brotherhood steam turbine driven by main engine exhaust heat. That gives a total hotel and operational electrical load capacity of 29 megawatts power required to run the navigation systems, the radar suite, the fuel heating and transfer pumps, the freshwater generators, the reefer container connections for 1,000 refrigerated boxes, the ballast system, and the steering gear hydraulics. 2 9-megawatt electric motors mounted on the main propeller shaft can augment propulsion directly, meaning the ship's electrical grid and its propulsion are not independent systems, but deeply coupled ones. A main engine shutdown does not merely stop the propeller. It collapses the exhaust heat recovery system, removes 8.5 megawatts from the electrical bus, and forces the auxiliary generators to absorb that load instantaneously or trip-on overload themselves. The Dali's electrical architecture exposed this vulnerability at the worst possible moment. Her MAN-B and W9S9 OME-C9.2 main engine, rated at 41,480 kilowatts, fed a single-shaft fixed-pitch propeller. Her auxiliary power came from 2 generators rated at 3,840 kilowatts and 2 at 4,400 kilowatts, connected to a 6,600-volt high-voltage main bus. When the electrical system failed twice in 4 minutes on departure from Baltimore, the 3,000-kilowatt bow thruster went dead, the steering gear lost hydraulic pressure, and a vessel displacing nearly 149,000 tons continued forward on residual momentum at approximately 8 knots with no directional control. The crew dropped anchor. The anchor did not hold. At that mass and that speed, no anchor on any ship in service could have held. The continuous operation of a large marine diesel is not a choice made for efficiency. Alone, It is the baseline condition that every other system aboard the vessel requires to exist. The turning gear, an electric motor that slowly rotates the crankshaft at approximately 1 revolution per minute, must be engaged whenever the engine is stopped in port to prevent the shaft from developing a permanent bow under its own weight. The jacket water preheating system must circulate 60 to 80 degree coolant through the engine block continuously during any shutdown period, lasting more than a few hours. The lube oil must remain circulating through the crosshead bearings, the main bearings, and the piston cooling galleries even when the engine is not firing, because static oil allows varnish deposits and corrosion to form on bearing surfaces, machined to tolerances measured in micrometers. Every one of these systems draws electrical power from auxiliary generators that burn their own fuel, meaning a stopped main engine does not save the ship money. It merely transfers the fuel cost from propulsion to preservation, while adding mechanical risk with every hour the metal cools. At her service speed of 25.5 knots, the Mærsk's turning circle has a diameter of 1.5 kilometers. Without engine power to maintain rudder authority, because a rudder only steers when water flows past it, that turning circle becomes infinite. The ship proceeds in whatever direction momentum and current dictate, a drifting object massing over 200,000 tons, fully laden, subject to wind loads across the hull, whose windage area exceeds 6,000 square meters. When the bridge sways 35 meters at a 20-degree roll, the officers on watch can see the horizon tilt, but cannot alter the ship's heading by a single degree without flow across the rudder. The engine is not an accessory to navigation. It is navigation. Without it, the vessel is not a ship. It is debris with a keel.